to end our discussion of sections 3.2 and 3.3, I'm going to give you a capstone question, okay? We are going to look at two people, Bob and Bonita, and each person saves for retirement according to the conditions outlined in parts A and B. And based on how they save their money, we're going to figure out who has more money for retirement, Bob or Bonita, okay? This example is great, okay? It will help you see if you really understand the difference between compound interest and the future value of an annuity formula. If you know when to use which formula, if you know how to use each formula. So it is a really good question, okay? So let's go ahead and read it and start working on it. So consider the retirement savings plans of both Bob and Bonita outlined below. Bob makes his first $1,000 deposit into an IRA, which stands for Individual Retirement Account, earning 6.4% compounded annually on his 24th birthday, and his last $1,000 deposit on his 35th birthday, which is 12 equal deposits in all. With no additional deposits, the money in the IRA continues to earn 6.4% interest compounded annually until Bob retires on his 65th birthday. How much money is in the IRA when Bob retires? Okay, so this outlines how Bob is saving for retirement. So we're trying to figure out when he retires, how much money is in his retirement account. Okay, so if you read this very carefully, okay, Bob kind of does two things, okay? So he is making these $1,000 deposits and he's making them annually. He starts on his 24th birthday and he continues to deposit $1,000 yearly or annually until he makes the last deposit on his 35th birthday. And then after that, he makes no additional deposits and he just lets the money sit there and earn interest until he retires on his 65th birthday. Okay, so there's two different things going on. Okay, so let's write down what's going on. Let's look at what happens between the ages of 24 to 35. Okay, so during this time, Bob is making regular deposits. Okay, so he's saving money, regular deposits. This is going to be the annuity. So we're going to use the future value of an annuity. So we need to use this formula. Okay, so that's what we need to work on right here. Okay, so we are looking for basically the account balance. Okay, this is going to give us the account balance up until he changes gears and then just lets the money sit there. Okay, so this is not the final account balance, meaning this is not going to calculate the account balance at age 65. This is just up until he stops making the regular deposits. Okay, so let's go ahead and plug in for this. I'll keep track of the variables over here because you are solving for A. Okay, so P is going to be the amount of each deposit. If you read it carefully, like I said, he's depositing $1,000 every time. Okay, so R, the interest rate remains the same throughout the problem, so it's going to be 6.4%. So the M value to notice here, he is making annual deposits and the interest is compounded annually. Those two things should coincide, so the M value is going to be 1. Time might be a little tricky here. It says that he makes the first deposit on his 24th birthday and the last on his 35th birthday. And so it tells you that it is 12 deposits in all. Okay. So if you actually count, and I'm going to pull out my hands here. So like, it's like 20, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35. So it is going to be 12 years for this. Okay. All right, so we're going to plug into this. Okay, so we're going to get, let's see here, 1,000 times 1 plus 0.064 divided by 1 raised to the 1 times 12 minus 1 all over R over M. Okay, so this will give us, this will cover through age 35. Okay, so we need to plug this in to get the balance. Okay, so let's go ahead and do that over here. So remember how you want to work with this formula. Okay, let's start in the brackets in the numerator. Okay, so we're going to get 1 plus 0.064 divided by 1 raised to the 1 times 12 minus 1. That's the numerator. Okay, hit your division key, put your denominator in parentheses if you don't do it in your head. Okay, this is what's in brackets. Okay, and then we need to multiply by 1,000. Okay, and so this is going to be, this brings him to age 35. Okay, so I'm going to go ahead and write down this entire number for your records. Okay, then we'll talk about how to go from here. Okay, so let's see here. So this is going to equal $17,269, and then I'll write out the full decimal. Okay, so at this point, he changes gears about how he's saving. He no longer makes the $1,000 deposits every year. Okay, he's going to let the money sit there. Okay, so at the end of this little era, I guess, when he stops making the deposits, suppose he got a bank statement. Okay, he would get a bank statement for a balance of $17,269.22. Okay, so once he stops making the deposits, this is the amount in the account. Okay, so this is the amount that will earn interest until age 65. Okay, so it now turns into a compound interest problem. Okay, so now we'll put then until age 65, the money is just going to sit there and earn interest. Okay, so it becomes a compound interest problem. So we're going to change to this formula. There are no more regular deposits. Okay, so we have to figure out the values of all the variables before we can plug in. Okay, we're still looking for that account balance at age 65 here. Okay, the p-value is going to be the amount of the one lump sum that's being deposited. That's where we left off. Okay, so that's going to be this amount. And then the R value will remain the same. The M value will remain the same. Even though we don't have annual deposits, the interest is still compounded annually. So we still need an M value. And the time changes now. The money is going to sit there. Okay. He made his last deposit on his 35th birthday. And then after that, we're trying to figure out what's going on until his 65th birthday. Okay, so time's going to be from 35 to 65, or I guess actually it should be from 36 to 65. Okay, so that is 30 years. Okay, because if if you get your hands out and you do 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, that's 10 years right there. And so, you keep adding the 20. I guess you could count the whole thing on your hands. Okay, so seriously. Okay, let me back up here. Okay, so ages 24 to 35. Okay, that's a total of 12 years. I've already counted that on my fingers. Okay, so I'll put right here, that's 12 years. Okay, and so then after age 35, he lets it sit there, okay, until age 65. So this is going to be ages 36 to 65. Okay, and this is a mess. And you know, it's really great watching my fingers on the video, but you can count out the ages 36 to 65. Okay, so you can do, let me do it again because I quit. 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65. So it's 30 years, and I need a manicure apparently. So let's plug all this in. Okay, so we're looking for the A values. Okay, so it's going to be the $17,269.22 times 1 plus, I'm trying to squeeze it in. Okay, the R value over the M value to the 1 times 30. Yay, okay. So we just need to plug all of this stuff into the calculator. Okay, let me draw my little partition. All right, so plug it in, and that's going to give us the account balance after, well, at age 65. Okay, plug in. Okay, so let's see, we left off here. I'm going to go ahead and clear it out. So $17,269.22 times 1 plus 0.064 divided by 1. You can do the exponent in your head. If not, put it in parentheses. So that will be the account balance at age 65 for Bob. Okay, so let's go ahead and write this down. Okay, so $111,050, and then we'll have to round. Okay, so we're going to round to the nearest cent. So this 6 right here will bump up. So Bob will have $111,050.77. Okay, at retirement. Okay, so now we've got to look at Bonita. Okay, so let's move on to part B. Okay, Bonita procrastinates and does not make her first $1,000 deposit into an IRA until she is 36. But then she continues to deposit $1,000 each year until she is 65. And they're nice here. You don't have to count with your fingers. They tell you it's 30 deposits in all. If Bonita's IRA also earns 6.4% compounded annually, how much is in her IRA when she makes her last deposit on her 65th birthday? Okay, so Bonita's doing things a little bit differently. Bob started saving at age 24. Bonita procrastinates until age 36. The difference here, I mean, we've got the same interest rate. We're making annual deposits. Interest is compounded annually, so that parameter is the same. So she is going to make regular deposits of $1,000 every year from ages 36 to 65. I don't think you want to see me count on my fingers again. That is going to be a total of 30 years if you did count on your fingers. So she, the whole time, nothing changes. She's making regular deposits the entire time she's saving. So we only need to use one formula here instead of two. Remember with Bob, we had to change gears because he only made regular deposits for the first 12 years. Okay. So for Bonita, we can use the future value of an annuity formula the entire time. Okay, so we'll do this. And then we know we're looking for her account balance at age 65. Okay. P is the amount of each deposit, which is $1,000. And then same interest rate that Bob has. And then we know M is 1 because she's making annual deposits and the interest is compounded annually. Time is going to be from ages 36 to 65. You can count on your fingers. They already counted it for you. It is 30 years. Okay. And you just pop this in, and this will give us how much Bonita has for retirement. Okay, so we're going to get 1,000 times 1 plus 0.064 divided by 1 raised to the 1 times 30 power minus 1 divided by 0.064 divided by 1. Okay, let's pop this in the calculator. Okay. All right. So again, with this formula, we're going to start inside the brackets in the numerator. So open parentheses, 1 plus 0.064 divided by 1 raised to the 1 times 30 power, close parentheses, minus 1 gives us the numerator. Okay. Divide by the denominator. Put the denominator in parentheses if you don't do it in your head. Okay. This 84.85 ... number is what's in brackets. Okay. You need to multiply that quantity by 1,000 to get the account balance. Okay. So Bonita is going to save $84,852, and if you round, 51 cents. Okay, so there's the full decimal. Okay, again, 51 cents. Look at the number that comes after it, which is a 0. So you do not round up. Okay, so here's her account balance. Okay, so this is how much she has at age 65. This is how much Bob has at age 65. Part C asks who has more money for retirement. The answer is Bob. Okay. Notice how much each person contributed. Okay. Basically, Bonita put in $1,000 every year for 30 years, so she contributed $30,000 out of her pocket. Bob contributed $1,000 every year for 12 years, so he only, gave $12,000 out of his pocket. But look at the difference. Just from saving so much earlier, starting at age 24 as opposed to age 36, look how much money, much more money Bob has than Bonita. Okay, so this is a great example that, again, you always hear, save early, save early, save early for retirement. That this really shows you, that is very true, and it shows you the power of interest.